Here's a long sequence of bits, 32 bits to be exact. Now, if you'd like to take the time, you can interpret this sequence of bits as an integer in decimal. If you do it correctly, you should get the following answer: 190,486,628 in base 10. Now, this would be the case whether you interpreted this as an unsigned integer, in which case you can only have positive values, or as a signed integer, in which case this first 0 would indicate that it's a positive number. The largest possible number that can be represented if we interpret this as an unsigned value would be 2 raised to the 32 minus 1. However, we generally interpret these as signed values, so if we interpret the sequence of bits as a signed number, for example, using 2's complement, then the highest possible value we can represent is only 2 to the 31 minus 1. Now, that's a pretty big value. In fact, this result here is the following. However, as large as that is, we might want to do computations with larger numbers. Additionally, and perhaps more frequently, we sometimes want to do computation with fractional numbers, or numbers with digits to the right of the ones position. And we can't do that if we use all of these bits in this fashion. Now, we've already talked about fractional binary, and one thing we could do is just pick some point in here to always place a binary point. For example, if we put a point here, splitting this in half, we have 16 bits there and 16 bits there. In that case, the interpretation, let's see, and once again, this is something you can try on your own first. This number would equal 2906 before the decimal, or the binary point. And then after, we would have this long sequence, 595, 2, 7, 5, 8, 7, 8, 9, 0, 6, 2, 5. So this would work. We could represent certain fractional values, and we could also represent whole numbers if we simply make all of these bits be 0. However, we have, of course, given up on the range of numbers we can represent, because now we only have either 16 bits to represent an unsigned value, or 15 bits to represent a signed value. So, although we now have a whole range of fractional values we can represent, we've lost the ability to represent many larger values. We can't represent this value anymore, or this one. So what we would like is a representation of numbers that gives us more flexibility. We want to represent the very large numbers and the very small numbers, and we can accomplish that by using scientific notation. Now, in decimal, you've no doubt seen something like the following: 5.32 times 10 raised to the 30. So if I were to expand this, it would be 5 3, 2, and I'd be moving the decimal. So the decimal point was here, but now I'd be moving it over 30 positions. So 1, 2, and now 28 zeros. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So that's a long number. In this form, it takes 31 digits. But in this form, it only takes 1, 2, 3, 4, 5, 6, 7 digits. However, I know that I'm working in base 10. So this 10 here is kind of redundant. So I could really reduce this to just these three here, 1, 2, 3, and the exponent. So I really only need 5 digits to represent this number, so long as I am using some sort of convention that makes it clear which digits I need and which ones are always going to be there. So a similar representation can give us numbers in binary. We can take, for example, 1.011, but instead of multiplying it by 10 raised to some power, I would multiply it by 2 raised to some binary number, like 11001. Now here, we can interpret this number in binary, and we first need to know that this number here, 11001 base 2, is 25 base 10. Now, when you multiply a decimal number by 10, you simply shift over the decimal point, or add a 0 to the right side. That's because decimal numbers are base 10 numbers. Because binary numbers are base 2 numbers, multiplying a binary number by 2 does the same thing. You move the binary point over, or you add a 0 to the right-hand side of the number. So multiplying by 2 shifts the number over by 1 position. That means that if we start with this number, 1011, initially there was a binary point here. We are multiplying it by 2 raised to the 25. So we're going to shift over that point 25 times. So the first 3, so we have 1, 2, 3, and then we continue. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So this number and this number are the same, but this representation takes up far fewer digits. Now the details of this are a bit complicated and will be clarified in the next module. But one final bit of information which I would like to make sure you understand is what these values are in decimal. There are 2 ways to compute this result. You can either note that 1.011 in base 2 is equal to 1.375 in decimal. That's a computation you should be able to do from the previous module. And if we do 1.375 times 2 raised to 25, the result will be 461,373,44. Now we can check this by taking this number and converting it into decimal. So turns out this position here corresponds to 2 to the 22nd. This is 2 to the 23rd. You can count this out from the right side. And this is 2 to the 25th. If you add these three numbers together, the result will also be 46137,344.